Hi everyone, welcome back to Math 261. This is Scott. Let's get started. So what we are going to be doing now is picking up with the subject of orthogonality, and in particular we're going to look at some of the consequences that orthogonality has if we're talking about sets. So orthogonal sets. Alright, so the setup here is we are going to have a collection of vectors in Rn. So we're going to say that they're going to be called U. There's going to be a few of them. Let's say up to UP. We're going to call the set S, S for set. In Rn. Okay, well, let's go ahead and peel the band-aid off. What does it mean for a set to be orthogonal? So a set is orthogonal if each pair of elements is orthogonal. In other words, the dot product is 0, i.e. has dot product of 0. Alright, well, so in other words, they have to be pairwise orthogonal, is the way this is worded. So let's quickly try a couple sets on for size, see what we think. So example, are the following sets orthogonal? Alright, so let's say let's say that U1 is equal to 3, 1, 1. U2 is equal to negative 1, 2, 1. And U3 is equal to 1, 0, negative 3. And then the set in question is going to be S, which is going to be the set comprising these three elements, U1, U2, U3. Alright, well, I just gotta compute them pair by pair. So U1 dot U2. So it's just a dot product, so it's going to be 3 times negative 1 plus 1 times 2 plus 1 times 1. And that equals negative 3 plus 2 plus 1 equals 0. Check. So U1 dot U2 checks out. Alright, how about U1 dot U3? So it's going to be 3 times 1 plus 0, or 1 times 0, plus 1 times negative 3, which equals 0. Check. Alright, so far so good. Two pairs are checked out, and the only pair that's left is U2 dot U3. So here we go, and we've got negative 1 times 1 2 times 0 plus 1 times negative 3, which does not equal 0. Okay, so the answer is not an orthogonal set. Almost. 2 out of 3. Alright, well, let's try again. Let's try a different set. See if this one will be orthogonal. So, what we will now look at for part B will be these three vectors. U1 will equal 3, 1, 1. So we'll just recycle U1 from before. U2 will equal negative 1, 2, 1. We'll just recycle the U2 from before. Now it's the U3 will change. So until we got to the last step, we had smooth sailing. So let's just alter this last vector and see what we get. So negative 1, negative 4, negative 7, for example, let's try that. And then the set in question will be S, which comprises these three. So U1, U2, U3. Alright. Well, U1, U.U2, we already did that. But just for the sake of posterity, 3 dot negative 1 plus 1 times 2 plus 1 times 1 equals 0. Check. Alright, how about U2? Sorry, U1 dot U3. So this one we don't know, because last time it was okay, but we just changed our U3, so maybe it won't work anymore. Let's find out. So we'll have 3 times negative 1 plus 1 times negative 4 plus 1 times 7. So that's going to be negative 3. Make that negative 7 plus 7. Adds up to 0. Check. Alright. Now we're in the all-important make or break third round here. So far, too good. Let's see if this one can also be good. So negative 1 times negative 1 plus 2 times negative 4 plus 1 times 7. And what we've got here is 1 minus 8, so it makes negative 7, plus 7 equals 0. Check. See the answer? Yes. The set is orthogonal. Okay, so it is orthogonal. Big deal. What good is it being orthogonal? Well, here's a theorem that will tell us what good it is being orthogonal. Theorem. Any orthogonal set of non-zero vectors, so as long as just none of the u's are equal to the zero vector, is linearly independent. So in other words, if we have such a set, it forms a basis for a subset, or for a subspace. So this means that, i.e., any orthogonal set of non-zero vectors forms a basis for a subspace But better yet, what if we have enough that it doesn't have to be sub anything, it can just be the space. And if we have n non-zero orthogonal, let's say mutually orthogonal, we have n non-zero mutually orthogonal vectors in Rn. So in other words, if we're talking about R3, we should have 3 of them. They form a basis. For R3, and we call it an orthogonal basis. For obvious reasons. All right, interesting. But it gets more interesting. So here is a follow-up theorem. If S, which is equal to U1 up through UN, so in other words we have n of them, is an orthogonal basis for Rn, then any vector x in Rn can be expressed as a linear combination and that linear combination would be of the form x equals c1 u1 plus dot 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 up to cn un, like so. Now, so far, you should be saying to yourself, yawn. This is nothing new. I already would have known that without any orthogonal, schmorthogonal, anything. If this is just a basis, this is true, let alone it being an orthogonal basis. So here's where the orthogonality comes in. Where Ci is equal to x dot ui divided by ui dotted itself. So in other words, what this means is we have got an express recipe. So this is a recipe for the weights of the UI. So we have got an immediate way of finding a recipe for these weights. Now, we could have found these weights using some older techniques of, say, row reducing, things like that. But it turns out we don't actually need to do that. We have an improved way of finding these things. Let's take it out for a spin, shall we? So here is how this kind of thing can appear. So we might have something like this. So we'll be given some vectors, perhaps. So u1 is equal to, let's say, 3, negative 3, 0. u2 is going to equal 2, 2, negative 1. And then let's say that u3 is equal to 1, 1, 4. Alright. And S is going to be the set comprising these. u1, u2, and u3. Okay. Now, here's the question. A. Show that S is an orthogonal basis. Oops. So easy to overlook letters in that. Orthogonal basis. For R3, so that'll be step 1, and in step 2 we'll be given another vector. So let's just focus on this first. Well, let's focus on the orthogonal to begin with. So u1 dot u2 is equal to 3 times 2 plus negative 3 times 2 plus 0, which by my calculations will equal 0. Check. u1 dot u3 will be, looks like 3 times 1 plus negative 3 times 1 plus 0, which will equal 0. Check. And let's check with u2 and u3. So u2 dot u3 is equal to 2 times 1 plus 2 times 1 plus negative 1 times 4, which is going to equal 4 minus 4 equals 0. Check. Okay, so it is indeed an orthogonal basis for R3. Now let's let the magic of orthogonal bases work for us. So if we look here, we can find that the weights are all going to be a matter of dot products of x with u and u with itself. So what we need is an x. So now B, express x, which equals 5, negative 3, 1. It's a linear combination of the u, the ui. Okay. Well, this is the kind of thing that we could have done already before we ever set foot in here. But now we can do this with this new expedited method. So we can just start calculating according to the formula for the CI. So that's going to be x dot u1 divided by u1 scratch that. Let's just take it piece by piece here. X dot u1. That'll be piece number 1 here. So x dot u1. So what we're going to do is we're just going to take the pieces of x and the piece in the components of u1 and multiply them and see what we get. Okay, we're going to have 5 times 3 plus negative 3 times negative 3 plus 0, which is going to end up equaling 15 plus 9, so that's 24. And then u1 dot u1. That's going to be 3 times 3 plus negative 3 times negative 3, in other words, negative 3 squared, plus 0, so that's going to be 9 times 9 is going to be, or 9 plus 9 is going to be 18, and so then that means that C1 is going to equal 24 over 18, or if we reduce that a little bit, that would be dividing by 6, say, that would be 4/3. Okay. So that's the first weight. The second weight, we'll come across by just doing x times u2. X dot u2. So x is 5 times 2 plus negative 3 times 2 plus 1 times negative 1. These are the components of x and the components of u2. And what are we going to get here? It's going to be 10 minus 6, make that minus 7, so it's going to be a total of 3. And as for u2 dotted with itself, which if you remember from the last section is the same as the magnitude of u2 squared, that's going to be 2 times 2 plus 2 times 2 plus negative 1 times negative 1. In other words, 2 squared plus 2 squared plus negative 1 squared, which is going to equal 9. Which means then C2 is going to equal 3 over 9, or in other words, 1/3. And then finally, x dot u3. So that's going to be, let's see, 5 times 1 plus negative 3 times 1 plus 1 times 4, which is going to equal 5 minus 3 makes 2 plus 4 makes 6. And then u3 dotted with itself, in other words, its magnitude squared, it's going to be 1 squared. So 1 times 1 plus 1 times 1 plus 4 times 4, which is going to equal 18, which gives us a C3, which is equal to 6 over 18, or in other words, 1/3. So what this then means is that x, in terms of the u's, can be expressed as follows. So x, the vector. X is equal to, it was 4/3 u1 plus 1/3 u2 plus 1/3 u3. And we can check this because we know what all this means and we know how it should end up playing out. This means that if I did 4/3 times the vector, which was 3, negative 3, 0, plus 1/3 times the vector, that was 2, 2, 1, negative 1 I should say, plus 1/3 times the vector, that was 1, 1, 4. If these are correct, then what I should get would be x, which was 5, negative 3, and 1. So let's think about this. So 4/3 times 3 is 4, plus 2/3 plus 1/3 means 4 plus 1 equals 5. So yep, 5. It's good. We have negative 1, sorry, negative 4 I should say. Negative 4 plus 2/3 plus 1/3. So it's going to be negative 3, sure enough. and 0, negative 1/3 plus 4/3 is going to equal 1, sure enough. And check. All right, so this gives us a way of finding the weights without having to do the big row reduction or any bulky thing like that, or find an inverse matrix or any of the other alternative approaches that we could have done. And a note here, the same formula for the weights applies if S is merely a subspace of Rn which contains X. So if S is merely a subspace which contains X, we can do the same thing to get the component of each of the basis elements. Now, what if it doesn't contain X? Well, then what we can do is what's called an orthogonal projection. Oh, actually, before we go on here, let's discuss why this actually works. So, why this works. So let's think about this. Let's think about what X dot UI would actually look like. So X dot UI. So this is going to be C1 U1 plus dot 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 up to CN UN, all dotted with UI. But the UI are all orthogonal to each other. So they'll all cancel but one. In particular, so this X dot UI, it's going to be, we can distribute this, and it's going to be C1 U1 dot UI plus dot 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 plus CI UI dot UI plus dot dot dot, and then we get to the very last one, CN UN dot UI, and basically this is going to be 0 and this is going to be 0, which means everything is going to be 0 except the one where the U's match. So X dot UI is equal to CI UI dot UI, which means that if I divide both sides by this, then CI is equal to X dot ui divided by ui dot ui. So that's just a little parenthetical aside. That's why being orthogonal makes the difference here, is that it causes all of the terms to cancel except the ones that match, which then lead us to be able to peel off the actual coefficient, the actual weight in this particular case. All right, now let's talk about orthogonal projections. So here's the setup. So we have some vector u. In Rn. And if u is not equal to 0, which we'll just assume that's not the 0 vector, so then there is a line that, that u generates. So then the span of u is a line through the origin going the direction of u, the direction indicated by u. So just thinking about this, let's say we're talking about like R2, for example, we've got u going that way. Then the span of u would be the line that goes all directions forward and backward from u. So it goes infinitely far, forward and backward from u. Okay. We also have a vector y, which is not on the line. Not on the line. So in other words, y does not belong to the span of u. So let's say we are going to be going like that. Okay. Then what we can do is we can find the projection, like the shadow. Actually, I'm going to draw my y slightly longer to make my point more clear. So then we can find the shadow that y casts on the line and by cast on the line we mean at a right angle. At a right angle to the line. This is called the orthogonal projection of y onto the line. And the way we write it is, we write y hat to mean this orthogonal projection, and it's equal to the projection on L, where L is this line, of y, where L equals span of u, and we can actually find this can be calculated. Y is equal to, and here it is the exact same formula that we used a second ago for the weights. So it's going to be y dot u, so there's only one u this time, divided by u dot itself times, oops, not times that, times u. So this will make a number, this will make a number, and together this will make a number times u. Now here's what this all means geometrically. Geometrically. Okay, so we're going to zoom way in here. So let's say we had u going like this. And so then that made a line, generates a line, which is the span of u. But we also had an unrelated vector y, which was not on the span of u, so not on the line. And then if we project this down, we find the shadow of that line onto here, then this is equal to the projection onto L of y, which is equal to y hat. This is not to be confused with a unit vector. Unit vector notation. This is a separate notation specifically for orthogonal projections. So, what we then have here is we have this, and note, y hat also gives the closest point on the line. To y. All right, then, and if we, so we have this close distance to the line, and the actual difference between them, z, which is equal to y minus y hat, oops, y minus y hat, is the component of y orthogonal to u. So what this means is, so thus, we can decompose y into two vectors, y hat, and this one is parallel to u, and z, and this is orthogonal to u. So the z up here would be this. It would be the vector that goes from here up to there. And y, what I mean by decompose is y equals y hat plus z, and that's by the definition of z. So this is commonly done in, for example, physics, when you want to decompose a force based on, say, what's called the normal force, which is the force that is going perpendicularly out of the surface. But for us, we're going to be looking at it in a little bit less exacting detail. We're going to just be doing things in a very bare bones schematic way, such as the following example. Let's say that what we have is y, which is going to equal, let's say, 1, 7. And let's say u is going to equal 2, 2. Okay. Now, question A. Find the orthogonal projection of y onto the line through u and the origin. i.e. span of u. Alright, so what this just wants is for us to find y hat. And y hat is just the same as finding the weight of y, considering this as the one and only element of a basis of a subspace. So then y hat, which is what we want, which is the projection onto the line here of y, is equal to y dot u divided by u dotted with itself. So let's figure out what these pieces all are. So y dot u, that's going to be 1 times 2 plus 7 times 2, which looks like it's going to be 16. And then u dotted with itself is going to be 2 dot 2, or 2 times 2 plus 2 times 2, which is just going to equal 8. And so what we're, and then this all times u. And so then what this gives us is the weight Ci, which is going to be equal to 16 over 8 times u, which is going to be, in other words, 2 times u, which is going to be 2 times 2 over 2, 2, 2, 2, which is going to be 4, 4. So this is the projection of y onto the line generated by u. by projection, I mean the orthogonal projection. But that's always what we'll mean when we say projection. Okay, now B will be decompose Y into a sum of two vectors. One of which is parallel to you, and the other of which is orthogonal. Is orthogonal to you. Alright, well, half of this is already done. So we already know y hat is equal to 4, 4. All we need is the z, which is y minus y hat, which is then 1, 7 minus 4, 4, which will be negative 3, 3. So then y is equal to y hat plus z, as follows. And you'll notice that z, if you take the dot product of that with u, sure enough, it is perpendicular. Be negative 6 plus 6, and it will equal 0. All right. So now the final topic of this section is orthonormal sets. So here we are talking about orthogonal sets that have one extra condition, and that's that the components of the set have been normalized. So these are sets of mutually orthogonal vectors each of which has length 1. So this is the ortho part of it, and this is the normal part of it. So ortho meaning the orthogonal, and normal meaning it's all normalized to make length 1. Now, if we have a collection of non-zero mutually orthogonal vectors, and it's not orthonormal, we can normalize it by dividing each vector by its magnitude in order to get it to a length of 1. So, if we have a collection of non-zero orthogonal vectors, we can normalize it by dividing each vector by its length to create an orthonormal set. All right. let's have a look at this. So an example. Let's say that we have u1 is equal to 1, 2, 3. u2 is equal to -3, 0, 1. And let's say that u3 is equal to -1, 5, -3. And then a question, and then S is equal to the set u1, u2, u3. So the first question. Is S orthogonal? And is S orthonormal? So first off, is it orthogonal? Well, that's a question we know how to answer already. We just do u1 dot u2 and just do pairwise dot products, and hopefully we should get 0 each time. So what's this going to be? Quick calculation tells me -3 plus 3 equals 0. What about u1 dot u3? Quick calculation, we have -1 plus 10 minus 9. Looks like 0 to me. And we have u2 dot u3. So it's going to be -3 times -1 is +3, 0, -3 equals 0. So S is orthogonal. Is S orthonormal? Well, let's figure out the magnitudes of the three vectors. So u1 magnitudes are so it's going to be 1 squared plus 2 squared plus 3 squared. This is going to be square root of 14. So we already know it's not orthonormal, but we might as well figure out the rest because it'll come in handy for part B, trust me. So u2. So it's going to be 9 plus 1. It's going to be square root of 10. And the magnitude of u3 is equal to, so it's going to be 1 plus 25 plus 9 equals square root of 35. And so S is orthogonal, but not orthonormal. So this answered the orthogonal part, but it's not orthonormal. All right. B. Normalize. Normalize S. So in other words, create a new collection of vectors where we make unit vectors out of each of these. So u1 divided by the magnitude of u1 is going to equal 1 over root 14. 1, 2, 3. So 1 over root 14, 2 over root 14, 3 over root 14. U2, we'll just do the same thing, divided by its own magnitude, which we already found. It was unnecessary to have found it. We already had an answer to part A, but we had a feeling it might come in handy. By which I mean I had a feeling it might come in handy because I knew what was happening, because I'm the one writing the script. So we have this minus 3, 0, 1, which is equal to negative 3 over root 10, 0, and 1 over root 10. And then lastly, U3 divided by the magnitude of itself. So now what we have is going to be 1 over root 35 and negative 1, 5, negative 3, which is going to be negative 1 over root 35, 5 over root 35, and then negative 3 over root 35, and there we have now an orthonormal version. So we'll just express it as a set. We'll learn names for these things later on. So this is the orthonormal version of S. So there we go. And a basis for a vector space that is orthonormal is called an orthonormal basis. And it'll be a useful thing we will discover. So this set right up here that we just found is called, and it would be called an orthonormal basis for R3. Now, one last little thing to discuss, and that would be matrices with orthonormal columns. So, first off, matrices with orthonormal columns are called orthogonal matrices. And here are some of their properties. So, theorem. Properties of orthogonal orthogonal matrices. All right, so first off, 1. If, actually, let's go setup first. So setup. U is a square matrix. Actually, U does not have to be a square matrix. U can be any matrix. So U is m by n with orthonormal columns. And we'll have x and y are any elements of Rn. Okay, so here are some of the properties. 1. U transpose times U will just equal the identity. Now what that means is, thus, U inverse is just equal to U transpose. So this is a matrix where if you want to find the inverse of it, rather than having to go through the whole rigmarole that we had before, what you can do is actually just take the transpose, as in just like literally interchange column with row, row with column, and you've got yourself the inverse. So this, another word for this is that U is unitary. Now here's another property. We take the magnitude of U times vector x. That produces just the magnitude of vector x. In other words, U does not change the magnitude of x. That's what one of the effects of having the normalization does for you. So this means this first one is U is unitary. This one is saying U is an isometry, meaning that it doesn't change the lengths of any vectors. Isometric, meaning same measure. 3, U times x. So you do U times x, that makes a vector. You do the dot product of that with U times y, and that's going to be the same thing as just x times y. And then lastly here, I'll squeeze this one in. So U times x dotted with U times y equals 0 if and only if x dot y already equaled 0. So in other words, a unitary matrix won't take any two vectors that were not already orthogonal and send them to any vectors that are orthogonal. Okay, so these are properties. We're not going to dwell on them right now. I just wanted to get them in the record, and we'll explore some of the properties of these unitary matrices, in particular the niceness of this one right here, as we proceed into our further investigations of Chapter 6. But for now, it has been long enough, and so I will join me for the next episode of Math 261. Until then, bye!